Okay, Joe, I've already gone over some points about work and how it's separate from heat of reaction. In terms of work and closed systems, if work of an observable object of interest, a reaction, equals 0, then you're talking about a closed system. That's an essential definition. Work equals 0 with closed system. Now, what does that mean, closed system? It means that the internal energy, delta EI, depends only on the enthalpy of reaction. And in most problems that you would be involved with, that's simply delta H of the reaction. The work function, being P delta V, is pressure times 0 in a closed system. In the truest sense of the definition, a closed system is a system in which work equals 0. But in a kind of a subnote, work can't be 0 unless delta V is 0. So really we're defining work as 0 if and only if the change in volume in here is 0, and that would account for the 0 work expression. So anyway, I want to be sure that everybody has heard me on that issue. Okay, let's see. Now, as I indicated a few minutes ago, work is not always presented delta E equals Q plus W, which equals delta H of reaction, plus 2.5 delta V molar. It's not always presented like that. And I converted it to make it easier because the conversion is at standard conditions, 25 degrees in thermodynamics and 1 atmosphere. But you'll run into applications where you will have to simply apply the P delta V. And so that's what I threw this one in there for us. It's very simple, and since I gave you the work is P delta V and the pressure is 1 atmosphere, and you simply calculate delta V expanding from 22.4 to 24.5, 24.45 minus 22.40 is equal to an expansion of, I think it was 2.05 liters. 2.05 liters. And so your work function in terms of liter atmospheres is 1 atmosphere times whatever change in volume you measured. And so that's 2.05 liter atmospheres. Well, I gave you the conversion factor per 1 liter atmosphere, and that's 101.3 joules in this case, and I believe it came out 208 joules. Now, the problem was work done by 1 mole of ideal gas. It was just an ideal gas, so it's expanding. So reaction, work, expansion. Okay, so if we're expanding, what's the endothermic or exothermic? Exothermic, right. So we'd have to represent that as exothermic work and put a negative in, and that is looks like B choice for that problem right there. Any questions about that? So it's a little interpretive, but that's the point of the problem, giving it to you. When you have the heating curve, you recall we have heat flow in, endothermic, or out, exothermic on that axis, and this would be your temperature here, whatever temperature device you're using, and we usually use degrees Celsius. Well, if we take ice, that's the easiest one to comprehend and relate to. If we have a block of ice below melting point, you first have to warm it up to the melting point, Tm, and then melt the ice. Then once all of the ice is melted, you heat it up to its boiling point, and then you evaporate all of the liquid and then carry it on up to whatever limit you wish to apply. Well, this is a solid, liquid, and gas. These are called pure condensed phases, okay, and they have temperature changes in them. In the horizontal slopes, it is solid and liquid interface, two phases in contact. Up here is liquid and gas. Now in here, work would be zero because there's no volumes involved, and it's the heat here is the only thing that's involved. But if you're working up here, you have a transition from a liquid to a gas. The gas demonstrates a molar volume, so work is an expansion and is less than zero. If you're going left to right in the curve, and if you're going the other way, it's compression, and work is endothermic, squeezing the balloon thing. Okay, so when two phases are in contact, the reaction is endothermic. Well, sure, if you have ice here and you're melting it, it takes input of energy to melt it, and so that's an endothermic process, but work is zero. Up here, this is also an endothermic going left to right, but work does not equal zero. That kind of help, Jimmy? What we're looking at here is an acid solution poured in with a base solution, a reaction taking place here, and as a result, the thermometer, which is in the solution right there, is demonstrating an increasing temperature of 10 degrees Celsius. Now the question is, the reaction is generally described as occurring in an open or a closed system. Well, this is a two-solution phase reaction, and so there's no gases involved, so that would be what? Closed or open, guys? Open. Closed system. So say HCl aqueous plus sodium hydroxide aqueous goes to NaCl aqueous plus H2O liquid. Since there's no volume changes in the system, that is expansion compression because of gases, then work, which equals P delta V, becomes P times zero, which is of course zero, and so work doesn't come into it. But you can calculate a delta H of reaction, which is based on the measured temperature change. And if you have the specifics of whatever you mix, what acid and bases you mix together, you can calculate that delta H of reaction using the MC delta T equation. And since it's increasing in temperature, the thermometer is part of the surroundings, and so the surroundings receiving heat means it's receiving the heat from the reaction. That is, the reaction sending energy into the surroundings, and you have a device that's detecting, that's thermometer, that change those signals, heat flow, and so it's exothermic with respect to the system. That is your reaction. It's very important that you kind of get a perspective on this. You never ever put the measuring instrument, so to speak, in the system. Now that's loosely said. What you do is you put the measuring instrument in the surroundings and an appropriate location where it will receive the signal sent by the object of interest system. So this is a closed system. It's exothermic and C choice in that. Okay, number 4. I'm losing my. How much energy would be required to heat a 20-gram copper cylinder has a specific heat 0.40 joules per gram degree C, and your temperature initial 25 degrees C, temperature final equals 125 degrees C. Okay, now what do we use? This is one of the method of mixtures kind of problems in which you either have a temperature change or you don't. If you have a temperature change, which showing in here, the heat is an MC delta T problem, okay? And M is your mass, C is your specific heat, delta T is the differential between this. So the heat transfer in this one would be 20 grams times 0.40 joules per gram degree Celsius times 125 minus 25, or 100 degrees C. Celsius, grams drop out, we're left only with joules, and that's left with rounded off to 800 joules. Now, I made them all the same numbers. It didn't matter whether endothermic or exothermic, but I wanted you to calculate the energy flow based on the MC delta T. Now, if we're melting just to, well, the next one is that. Okay, let me give you, this is D. Okay, number 5 has to do with the heat of fusion of ice, delta HF, heat of fusion. Heat of vaporization is the evaporation kind of term. So 80 calories per gram, and the question is how much energy to melt a mass of ice, 100 grams. Well, there's no temperature change involved here. Simply melting, two phases in contact, liquid and solid. Until all of the solid is melted, then temperature will not change. It's like ice water. You put ice into water and you stir it or shake it till it reaches the thermal equilibrium, and it'll stay there until all the ice melts, and it'll warm back up or whatever. And this, of course, is the delta H, or Q. Let me keep using Q. Heat flow is delta H fusion times the mass whatever you're melting, and so that's 80 calories per gram times 100 grams, and it's 8,000 calories. Grams will drop out, and simply put, that 2 is a D choice. Okay.